I'm Cal. I'm a student in Dr. Yatow's lab at the Rowland Institute. And today I'm going to tell you about towards measurements of non-contact friction over suspended graphene, with towards being the keyword. So broadly speaking, friction is the set of processes that turns mechanical energy, motion, into thermal energy, heat. And in particular, in force microscopy, you're trying to use a harmonic oscillator like a cantilever to transduce some sensitive force, perhaps by looking at frequency shifts. It turns out that the sensitivity to force, the force noise spectral density, is limited by friction. It's proportional to the dissipation gamma, or inversely proportional to the quality factor of the cantilever. Therefore, for sensitive measurements, minimizing friction is really critical. So one particular form of friction that's of interest to ultrasensitive force microscopy, including magnetic resonance force microscopy, is what's called non-contact friction. It turns out that when you very closely approach the tip of a cantilever to a surface, the quality factor dramatically drops off with distance. And some excellent work in Dr. John Marone's group indicated that this is due to dielectric fluctuations that introduce varying electric forces on the tip and damp its oscillation. On this plot, you can see a comparison of the non-contact friction above gold, a thin polymer layer, and a thick polymer layer, showing increasing non-contact friction, respectively. So this is a very, very, very small force. The kind of friction that's typical in AFM measurements, for example, dragging an atomically sharp tungsten tip over a graphite surface, is on the order of 10 to the minus 7 newtons. The kind of forces that are relevant in non-contact friction are on the order of 10 to the minus 16 newtons. But it turns out that they have a pretty substantial effect. The intrinsic quality factor of the best scanning resonators available now, like the nano-ladder resonators that Ye was talking about earlier, is about 10 to the 6. But if you bring them 10 nanometers away from a surface, like you have to do to get high spatial resolution and high sensitivity to magnetic forces in magnetic resonance force microscopy, the quality factor drops off to about 10 to the 3rd. In fact, non-contact friction is the primary obstacle to single nucleon sensitivity force-detected magnetic resonance imaging, which would be a really cool thing to be able to do. And the reason for that is, with the best available devices in the absence of non-contact friction, we would have sufficient sensitivity to see single nuclear spins. So it's an interesting problem to see how to reduce non-contact friction. One thing that's been shown effective in the literature is reducing the area of the tip in proximity to the sample. However, there's only so far you can reduce the size for it to either have a magnetic tip or have a sample attached. So at some point, you have to find some other resolution. And the other option is to reduce the size of the surface that this tip scans over by making it thinner. One potential solution to that, as to with most other problems in nanotechnology, is the use of graphene. You could potentially do two graphenes, thin, extremely thin shape, and good mechanical properties, and electrical conductivity, which could screen out other electric fluctuations, use a suspended graphene sample stage for magnetic resonance force microscopy. So the goal of the project that I've been working on is to try to characterize that non-contact friction and see whether this would work. So the sample preparation for this project was particularly involved. We went on the internet and we found these graphene over holy silicon nitride grids designed for transmission electron microscopy. They have 2.5 micron holes on a 4.5 micron pitch covered with monolayer graphene. So we bought some of them. We broke them in half so that we had a clear surface to access with our microscope, and we stuck them to the sample stage. We've attempted to ground the graphene with conductive epoxy, so we can potentially do some electrical measurements like varying the tip sample voltage, but we haven't yet tested the efficacy of that grounding. For a probe, we're using an audio frequency cantilever made from single crystal silicon with a Q of about 10,000. These were made by Yingpan in our group via a photolithography process, which is a pretty exciting new way to enable bulk fabrication of these ultrasensitive scanning cantilevers. The radius of curvature of the tip is on the order of a micron. The measurements were conducted in a home-built high vacuum scanning probe microscope. Coarse positioning is achieved by piezoelectric steppers, fine positioning by piezoelectric scanners. The cantilever's motion can be excited with the shake piezo and read out with a laser interferometer. On the image on the left, you can see, if you look very closely at the top, the optical microscope view that we use to align the cantilevers to the sample. So the protocol that we're using for these measurements kind of has two steps. First, we approach the cantilever to the surface, and we detect the position of the surface by looking at the DC deflection of the, by looking at a DC change in the interferometer power caused by the cantilever deflecting, basically very crude pinpoint AFM. And then we'll lift up, and to measure the dissipation or the quality factor of the cantilever, we excite it by applying a pulse with the shake piezo at the resonant frequency, and then allowing the cantilever's motion to decay. The quality factor is proportional to the time constant of the exponential decay. So then we go and we repeat that measurement at several heights approaching the sample, and we see the quality factor decline until we finally hit the sample, and we don't see oscillation. So early this summer, we conducted some preliminary measurements with this system on a sample which consists of evaporated gold on silicon with trench geometry. And with a more primitive version of the measurement protocol, we were able to get reasonably good topographic data and also material contrast between the gold and silicon, kind of as we'd expect from prior work. The gold exhibited lower dissipation than the silicon did. Since then, we've made some improvements to the process with reducing the hysteresis from repeatedly moving up and down like we did in these measurements, and also automating selection of the parameters for the ring downs so that we can get good quality data with less measurement time. In the middle, though, we spent several weeks cleaning out some contamination in our vacuum system that resulted in substantial quality factor decay without any samples present. So that delayed the acquisition of the data I'm about to show you, some of which until about yesterday. So looking at this sample, the first thing that we did was measuring the topography using this touch map along that slice shown in red. And you can see that the surface looks pretty homogeneous. We also conducted a frequency scan measuring the frequency of the cantilever, moving it over the region and looking for any forces that change the cantilever's frequency. And you do see some effects, but it's pretty inconclusive. We need to get some more data, especially making sure that we're following the curved surface really well. The more interesting measurements that we did, though, were again, along the same line scan, measuring the dissipation as a function of cantilever sample standoff. And you can see a couple of sample dissipation curves on the left. We are able to get much finer resolution data at the cost of spending more time. And for these scanning measurements, it takes already a few minutes per point. So, but what's interesting is in the scanning measurement, you do see some kind of periodic structure with lattice spacing on the same order as the patterning of the suspended graphene holes. So that shows promise for future work and better characterization of the sample. So kind of the most immediate steps that we're going to take is to follow up on this with a larger 2D measurement and hopefully establish with some more confidence the nature of this pattern. We're also going to take a silicon nitride TEM grid without the graphene and repeat the same measurements as a control. In the more distant future, there are a couple of other non-contact friction related projects that we would like to continue into. There have been several previous papers on NCF, but most of them have been measurements with a single cantilever over one or a few materials. So we would like to get a more comprehensive library of non-contact friction data to better elucidate its mechanism and learn about how to engineer around it. So we've prepared cantilevers with as well as their native silicon tips, gold and iron cobalt nanowires attached with a micromanipulator under an optical microscope. And then with the collaboration of Ivan Shorubalko at EMPA in Switzerland, used a focused ion beam to mill the tips into a few different sizes and well-controlled shapes, so that we can control for tip area in non-contact friction measurements. We also have been, so this image in the middle is a fixture that I designed and built this summer that is used to clamp the cantilevers during focused ion beam milling so they don't oscillate, to allow better precision. That was kind of a fun project, given that each of the cubes are about 3/8 of an inch on a side. The other thing that we've been working on is preparing sample processing and sample concepts for a larger non-contact friction study. It's been found in the literature that annealing under vacuum can reduce the impurities in graphene and potentially reduce the non-contact friction. So we've built a heated sample stage to enable in situ thermal annealing of the graphene. And then we also are considering evaporating gold strips onto these graphene on silicon nitride membranes to provide another material, another relevant material against which non-contact friction can be measured in the same experiments. The other thing that we've been doing is working on the technology development for building a practical MRFM sample stage from suspended graphene. This is in collaboration with Laurel Anderson and the Kim group at Harvard Physics. Because ultimately, if you're to make a practical sample stage, it needs to incorporate radio frequency strip lines. So you're going to have to make it via some top-down technique. So we're working on building a transfer station for building up structures from 2D materials, and also attempting preliminary transfers. You can see right there the graphene all curled up over where we're trying to suspend it. So there's still a lot of learning to do. So I want to thank the other members of my lab, Ye, Kai, and Ying, the engineering staff at Rowland who supported this project, and then our collaborators. Any questions? Yes. So the number that I've seen cited is 200 C. I believe that the hardware in our sample stage is compatible with temperatures up to 400 C. So I imagine it's going to take some experimentation and more thorough literature research to find the optimal temperature. Yes?
You mentioned taking the data, you said at a few minutes time scale. How do you compensate or worry about the drift, worry about any drift or creep?
Yeah, so one measurement that we've done is just repeatedly doing this at the same point.
Okay.
And we see probably once the instrument is well thermalized, on the order of nanometer per minute or less drift, which is acceptable for these measurements. Yes?
So you know, these are amazingly flexible cantilevers, and I'm wondering if, as you bring them close to the surface without any additional excitation other than thermal, can you see that they behave far away like a free beam, and then as you come close, they become more like a suspended beam just from the thermal response?
So kind of the changes that you see in the spectrum of the thermally excited cantilever as you approach are first spectral broadening as the quality factor declines, and then after you touch, you see the original mode go away and a new mode corresponding to a clamped beam appear in the spectrum.
Right. Are you interested in Euler buckling at all? Would that, you would probably be in danger of breaking them, but
They're surprisingly compliant. You can compress them. They're about 150 microns long, and you can compress them by several microns without damage, since they're very soft and flexible.
thank you.
Sure.
Any other questions? If not, let's thank our speaker.